the lights. Okay, at first, let me thank you, Professor Jinghan Park, but he's not here. And and also, it's very nice to attend the first Lee Crystal conference. Usually, I feel a little bit nervous when I come to give a talk in a lot of experts in this area. But the good thing is, after the Peter, he said the Oseen-Frank model is still the golden model, so it's okay. So it means I do something, still some physical meaning, but maybe not much. And so today I talking about my joint work with Professor Zhou Pingxin. It just appeared this year. And so Lee crystal is some phase between the solid and the liquid, and I think I cannot understand quite well in physics, but however in mathematics, it's my using notation like U is like your m, little n is the direction of the liquid, and so in mathematical formulation, so we study three-dimension domain or in R3. Okay, so of course in most cases I consider connected. I think then and also I study using mathematical point of view. We study like the energy function. The energy function, like the John pointed out, you need certify which space. So for example, so today I study like H1, like W12 space. For example, in physics, maybe some people study this H1 with a continuous function, then you get different results. So in mathematics, you talking about the mapping to, because the direction is the unit vector, so it's S2. And so this is a basic surface space the value in S2. And in physics, you defined by the total energy on this domain, omega. And the W is we call the Oseen-Frank density. So in physics, so Oseen-Frank density is decided by the four constants. I just realized, so here it's not right. So it should be K2 plus K4. So this is the divergence of U and plus K2, U dot curve and U cross curve. So there, I think for three, the constant you have physical meaning. Maybe K4 should be like your K4, the K2 plus K4, something like that. And the last time, if you do integration, because this is divergent fluid, if you do all the Lagrange equation, so this term is not a fact. So in this case, actually, we can rewrite the density by this. So we can rewrite the energy become a gradient of U plus V. So A is the infimum value K1, K2, K3. So the basic you're using this total energy is a number. Okay. Then so that case you can see very clearly, and a lot of people take this equal to 0 case. So that one is okay. So what is our Lagrange equation for Lee crystal energy? So this system is very complicated. It's of course if you only consider this term, so this disappeared. So that is no problem in the elliptic system. But however, if you have a constraint, then you have this term come out. But you using the strong convexity. So this term, the principal term, is elliptic, is no problem. But however, you involve this term. So this term depends on K2, K1, K3, the constant. So that case, you might be in general, you don't know is it elliptic system or not, because this is a minus sign. And then this a lot of cases is very complicated. So this is pointed out by Hart in his survey paper. So in general system, is not now elliptic system. because the reason, so this term will be a fact.
So why put W and V there? I mean, where's the A drive use word?
Like here, okay.
No, but that's part of the...
No, I explained to you. I think it's only thing for Laplace case, if you equal lambda u, then you dot the...
Yeah, I understand that, but I just don't understand where the A is. I mean, it's as if the...
A is the infimum of k1, k2, k3.
Where is it in the Euler-Lagrange equation? I don't see it in the Euler-Lagrange equation.
A is here. So this is totally, so this is a convex function, no problem. So if without this term, it's an elliptic system. But however, if you pass this term together, it's hard to say.
It's kind of strange. I mean, if you're going to write W like that, why didn't you write it entirely in terms of A and B, rather than in terms of W and V, so constant?
No, because the reason is the Laplace case is very simple. So this is the Laplace multiply is disappear. So the only thing effect is the difference. Because the K1, K2, K3 is the minimum value, you always can use in this the trace free. You can rewrite by this. So this is already pointed by Jaquinda and Hardlin in their paper. See. So of course the other term, like a gradient term, like harmonic maps. So it's the only thing, but the only thing. So this term you need to handle. Okay. All right, so I just mentioned, so the three constants is equal case, then you become like a harmonic maps equation, okay? So that case, this is a harmonic maps, there are a lot of results. Maybe I will mention a few results. So the first result is minimizing harmonic maps. In 3-dimension to S2, you can prove that minimizing the singular point is an isolated singular point. So you call the defect. That is an isolated point. And then for general model, is a hard Kindlina Lin, and after their paper, they proved. Of course, existence minimizing is no problem because you can. That's easy. But he proved that each minimizing of the general Oseen-Frank model is smooth except the small set of singular set. But they cannot prove the singular set is isolated. They only proved some Hausdorff measure beta less than 1. But however, there's no Lie singularity. Also, in mathematics, cannot say the isolated singularity. But of course, a lot of literature, the misunderstanding, they mentioned say the isolated singularity is not true. So still open problem for this model. If you minimize the Lie crystal energy, you cannot say the isolated singularity. It's not clear. So this is still open question. Okay, so today I don't want to go too far from that. I just to study the Lie crystal flow. It means the gradient flow, right? You have an energy function. I do first the gradient flow. The gradient flow with the Oseen-Frank model. So this is of course so far no physical meaning, but we'll come back later about the physical meaning. So gradient flow is a natural flow. It's like a rich flow, a lot of flow is not gradient. But a gradient flow, you have an energy function, then talking about gradient flow. So you do gradient flow. So this is a Lie crystal equation. Then you do a dt, like the decreasing. Then we try to flow this equation. What happens? So you do mathematics, right? So this is of course. So this is a system. But so far, it's not clear it's a parabolic or not, but it doesn't matter. The system is still okay. You can flow. And then my first results is, so of course, I would like to mention the Lie crystal flow is a prototype equation from Ellis and Leslie system. Then we come back to mention this, okay? And also, Lie crystal flow generalizes the harmonic maps to S2. So this is like because K1, K2, K3 equal is harmonic maps equation. So in that case, even 2-dimension, it will propose up a finite time. So I think from the harmonic maps, the most important the fundamental results by E.L. Sampson, then later on, there are a lot of results in this area. And but in today, I would like to mention the one result is relate my paper. I don't want to go away for this area. So the paper is by two-dimension case. It means 2D case is you can go R2 over the remaining surface. And Michael Stewart, he proved the flow global existent. It means you study energy. You can flow smooth solution up to some finite time t, then will blow up. Then he can flow again, then blow up. Then finally, so he proved the global existent except the totally finite singularity. So that is the results. I think my whole idea is from this paper. So he's from geometry paper, but he do more general case. So this is motivation from his paper. So in this talk, because I do 2D case, of course, the boundary, maybe you still can do it, but sometimes the boundary will cause more trouble. So you do R2 is a simple case, right? If, of course, later on, maybe you can do boundary case, then you need introduce some subject space. It means that infinitely you need going to constant, and that makes sense. So that case, so this is the idea. Then the first results, I said if you give in initial map from subject space, and then I can prove I have a global existent. Actually, this result is similar like Max Stewart one. So this is said I start the solution from here. Then I can flow solution to T1, blow up. So this is smooth. Then at this T1, you have a finite singularity. Oh my God. So you have finite singularity at T1. Then you flow again in T1, T2. Then you have another finite singularity. But they will finish some Tk. Then after that, no singularity. Because the reason, so at the T1, each T, so you have an energy concentration. So that means maybe it's a defect. Like you have an energy concentration in that point is a blow up. So that case, so this is so-called clarify the maximum time of TL. When each T, so the energy will be very large. So you must blow up. Then blow up, but the limit still exists. Then limit still belong to H2. Then you can flow again. Every time your total energy is finite. So then your singularity, in that case, you can prove is a finite singularity because you have another very nice local energy inequality. So this is first results. And then before I do first results, I would like to mention related physics. So in physics, in the 1960s, the Ellison, Leslie, I don't know who is first, both independent, they proved the hydrodynamic series of the liquid independent. The Ellison-Leslie series is a dynamic flow, like the Professor Doyle he mentioned, and Peter and the Professor Zhang he mentioned today. So it's a flow, and so in liquid store, so the V are using the velocity, vector, and U maybe it's not like the notation. U to the N are using the V because I use the map is always a V. So I keep the map. So this unit director. And then, so in fact, so this Ellison-Leslie system you write down exactly like this. So you look at here. So this last part is like a liquid flow, like a gradient flow for Oseen-Frank model. So except this V dot gradient U here. So, and so you look at here, the first two equations. So you forgot this part. Then this is the famous Navier-Stokes equation, and there's a lot of results. So the lambda you can choose in one. So that case, so this is actually Ellison-Leslie system. There is a COP, the really Oseen-Frank gradient flow plus Navier-Stokes equation. Of course, if you K1, K2, the K3 equal become harmonic maps and with no stocks. But in general case like this. Okay.
This is not exactly the Erkin-Leslie. This is just have the Erikson, didn't have the Leslie.
Yeah, but I understand the physics. Maybe you have more complicated model, but at least so this is one of still inside. Okay. Yeah, I not claim all like this, but I told you before I'm really worried about this part. So. But today I work in this maybe not a general Oseen-Leslie, but it's one part of that. Okay, so system. Okay, so that case you need so in mathematical point you're doing like zero boundary for velocity, and you delete your energy boundary, then you're doing this divergence must be equal 0, right? Then you can do that. But in my case, we don't have boundary, R2, okay. But if you, like yesterday, the Professor Lee, he mentioned the 3-dimension case. Okay, so Oseen-Leslie system, I mentioned is a Navier-Stokes coupled with a liquid crystal flow. And the study of the Navier-Stokes, they're very interesting, of course. They still have $1 million problem. Tremendous results by Navier-Stokes have been studied by Chef and Kafleri, Kohn, Nienberg, and Fanfa Lin, and Ken and Xin. They're all the papers that do a lot of results. But today, I need to constrain the existence of the solution for this system. Okay, so in mathematics, maybe someone knows this. You know, this the value of u equal 1, because it's a vector, right? Equal 1 is complicated. Then in mathematics, there's one physicist called Ginsburg-Landau function can approximate. So this is always people said, your original, the u is a value should be in S2. But however, from mathematical point of view, we can use an approximation model. So approximation model is said using a parameter epsilon. So you put this penalized term. So 1 minus u squared. You know, this epsilon tends to 0. If it's energy finite, it means the value of u will tend to 1. So this is very efficient in suggested by the physicists in superconductivity. So that case, Oseen system is complicated, and the people suggest using this approximation model to study. Okay, so that case, so in fact, this approximation model, every first two equations same like Oseen-Leslie system. So only the different one. So you look at this part is good because this W is a convex function. So this is exactly the parabolic system. It's okay. You can do any PD you like. Then so this is very nice. You can study this system to prove existence or partial like or smoothness is very simple. So in the case of K1, K2, K3 equal, 3 constant equal, and Fanfa Lin and Chun Liu, they proved the global existence, the 2-dimension case for the approximation model. He also proved some 3-dimension weak solution. And I think in another paper many years later, and Lin and Liu, they tried to study this asymptotic behavior, like the epsilon tends to 0, right? You only prove the approximation. Maybe physics said you are not a really model. You only study this model. So that case, he want to study if v epsilon and u epsilon is a solution. So what is happen for the limit behavior for epsilon tends to 0? Actually, the paper they mentioned so this problem is not clear. He cannot answer. He answered by some measures there. It's something it's not proved that the limit exactly satisfy original equation. So therefore, there is an open question for many years in this area, even 2-dimension case, and in their paper they cannot do it. And so just recently, so this is the system. So this is for simple case is this is like a Navier-Stokes with harmonic maps equation, and then the limited case what has happened for K1, K2, K3, and so it's independent to prove by myself and also by lin 1. They're doing general model for domain, and but however their proof is different. They're using different proof. I proof is basically I studied the limit, the epsilon tend to 0 case. Then so recently there are a lot of results for this system for 3 dimension, a lot of results. But I don't want to go through this part. So I just talking about the in general model. Okay, so this general Ellison list system, why it's not different with 3 constant different? Because you from the theory of the parabolic system, for example, by the Professor Armand's paper, the book, he mentioned no maximum principle. So in that case, if you do Laplace case, your maximum principle, you can do a lot of u. If your study is equal 1, then u will less than 1. So that effect is not true. Even for approximation model is not true. So and another thing different, if you look back this one, right? So if you look back this you look at this approximation model. If not equal, if this depend on u, so this time is depend on gradient u. So even from this equation, you cannot prove global existence. So that means sometimes you have trouble. You should be very careful to say it's the same thing. You mathematically need to verify everything what you said. So the basic in second part of my talk, I will use an idea, the first the theorem, then with some results for then I can prove. So this result. The theorem 2, you said you have a two u with 2 vectors, right? And if u belong to H1, v belong to L2, and satisfy the divergence we know equals 0, then I can prove I have a global solution in whole T and for the system. But however, I have one thing I didn't prove. From the modeling system, I can prove each time of T, the singular set is finite. But for this T, I only can prove the singular time is finite. The singular time of T, L is finite. But I cannot prove at this time the singular set is finite. But I only know the singular set will concentrate by this. So the density, so this is like a density, almost like a density. You know, the Oseen-Frank density almost like this, because the control, the low bound, so we know the less than epsilon. So I believe they're still open if at the singular time, the singular the singularity is finite or not, still open. So nobody knows. Another open question for this part is the solution is unique or not. Still, there are 2 open questions. This part, the singular time of finite singularity still not known, and also about the weak solution is unique or not is not known. For the simple model, like someone proved. So in that case, so this is 2 things really different. Okay, so now this is a mathematical sort of a conference. I just outline my approach and the first results. And so this equation is a little complicated. So this is so I think I don't want to argue about is it parabolic or not, but it's not a fact with me, because my approach, I don't want to use this. I'm not working in direct this equation. I'm using approximation model. So if you record here, if you're using PDE, you improve log existence, it's very complicated. You don't know how to do it. So in that case, I just using this Ginzburg-Landau flow. So in that case, so this is a parabolic equation. So of course, you using Sobolev approximation, we can assume initial value H2. Then you can approximate like then. And then you look at this modeling equation. So this is satisfy the parabolic system, and also this is a gradient square. But of course, you cannot say this you have a global solution. But however, from mathematics from the Russia the book, the Edelman, and also from Arman the book, then you can say that this is you give an initial value is you have a local existence. But however, you don't know the maximum time t. You don't know where stop. But if you want to pass limit, then you have two steps, right? Then you need for each epsilon you have a fixed length of t. Otherwise, you cannot do. If the epsilon gets 0, the t star, the local existence might be small. They cannot do any conversion. So basically, we try to study this the conversion. So conversion. So in that case, we need the follow some space. So this is a very nice space. You mean in the time space is L infinitely. So this is like from so-called Ladzinskaya the space. And then this is the second derivative. You need the integration with the t. So this space with the t is like L infinitely. So this people know that dt like gradient t is the same like in parabolic system. So we study this so-called V space. If you can prove V space, usually you expect the smoothness. So this is from the Ladzinskaya Volatseva the book. And for notation, so I defined E epsilon. So this is the original the Oseen-Frank the energy, but now we don't have a constraint. So you can go to R3, and then you plus the Ginzburg lambda approximation. Then you define this approximation the energy. Then because you produced the gradient flow, so you have a very nice this the energy decreasing. The energy we are decreasing. But how remember your initial value in L1. So that case, so this is very nice. So it's not depend on epsilon. In some sort, you must have a result pass limit from here. So now you from local existence, you know you have maximum time t epsilon. But however, you don't know t epsilon you have a uniform constant or not. So that case, we need to verify you have a uniform constant. So that case said you can prove that using this concentration before this concentration is smooth, is the same like the harmonic maps. Then you said that t tend to t capital T epsilon, then you are smooth. But the only thing we need to verify this capital T you have a low bound. Is a uniform bound, not depend on epsilon. So in that case, actually, so this is not so hard for this modeling model. So modeling model, the idea is from here. So you have a so-called local energy inequality. So that means you start initial value, okay? And the initial value, you always can set the R very small. So this is very small. Because the initial value, the map is given, R, because you can uniform. So this is less than epsilon. Then if R0 is fixed, then you can do T is depend on R. Then you have uniform here. So this means you can verify this no concentration by this local energy inequality. So, but however, this local energy inequality is not always true. For Edison system, it's not true. So we cannot prove such. We can prove a new version, but not like this. So this is a very nice one. So this is without the Navier-Stokes the part. So this is we can do that case. Then we found out we have a uniform the T1. So no concentration. So that case. So this case is not trouble. And so now the following above the local energy inequality, we can choose in for any small epsilon. We always can choose in R naught. So for example, this R less than R naught. So this is means no concentration. It doesn't matter it depends on epsilon or not. So that case. But now there's another trick. So you pass limit, then you have one term if you write down here. So this is I use a simple model, okay? But in this case, simple model is the same. You know, if you pass limit, you need to study this term. So this term, you only know. So this is finite. So this is from energy is finite. But however, in some case, we need to study proof this is finite. So this is a power 2. This is power 4. So if you look at from that part, I use an equation. If this u, the value between 1/2 and 2/3, then I can use an equation, take square, then they're controlled by the gradient square. So this is the key part. You need to study. So this value. So what is the number? U epsilon equal 1 is equal 1, right? Then you have a by continuous. You can extend like that. Then you can prove this quantity, this inequality is true for all t1. So now we try to verify that is true. So that case, is the original the approximation model depend on epsilon. You do rescaling, then you become this equation not depend on epsilon. You do rescaling. Then if you want to prove it's less than 1/2, I can say, so you can choose in the tau is the maximum time, right? In this after the scaling is less than 1/2. If this tau is before the t0, then if I can prove a continuous, then there must be t1, right? So in that case, then I using the tau is maximum, such that is true. Then I said the maximum, 1/2, 4, and 2. Then I can prove in this case come back 1/2 and 2, 3. Then we can continue. So we can do again. So that case we use this trick is like a continuous. Like then we prove the whole results. So basically the trick like here. Then we do rescaling. We using basic energy inequality still there, and so as a concentration. For this Ginzburg lambda model, it becomes like this. So this is said epsilon, and after rescaling. So here is you should do rescaling. That depends on epsilon. And then, so if no concentration like that, then you using mathematical integration by parts, right? Then I think now because this first part is elliptic system, you can do it. Then you keep the principal term. And only this term, so this term is not so bad. So this term is like a harmonic maps term. Harmonic maps term is the gradient power 4. You can control it by the second derivative term. And the only bad term from this part. So this term is a Ginzburg lambda term. So Ginzburg lambda term, for this is like a u dot 1 minus u square and times Laplace u. And so this is a very nice model. You just integration by parts. You get actually, so this guy actually is positive. So this could only this term. So this term, and then you have like a power 4 term. Right? Power 4 term. Then you can using Young inequality. You can put this 1 plus epsilon square term small. Then you using equation by trick become control like that. Then this power 4 term can control. Then everything control. So the trick is like that. So you using. So you using like Adama. So this is a principal parabolic term. Okay, is a convex. So this is a gradient square is okay. So this is a power. So now after Young inequality, so this eta is a very small constant. Then you get a 1 minus u theta square. And plus second derivative square. So this term, eta very small. So this term can be observed here. And actually this term also can be observed because it is the reason I know u is between 1/2 and 2, right? So the u square, like u is between here, then use the equation, then you can observe it become second derivative and plus and dt square. So and for this term, you just using so-called Lagrangian inequality. So this actually is controlled also by there. So in that case, you can get so this the derivative. It's nice. So it's basically you using the u is below 0 and bounded. Then using the approximation equation, then can control by that. And then I using this so-called Lagrangian inequality because the no concentration we can write down the integration of power 4 can controlled by the small epsilon. Small epsilon is means epsilon 1 is no concentration. And then, so this is a second derivative square. Then you plus Z1, then you can then control everything. Then finally, in fact, you can prove the second derivative is totally bounded by this. And then, and similar, you apply the Lorentz-Scalia inequality again, then you can prove this is also bounded. And then you know, so you rescaling back, you can get the second derivative is bounded in space. In space, L2 norm is bounded. So of course, by separate embedding, this is 2 dimension. So we know this this U must be Hall continuous, right? Hall continuous, and then you using Hall continuous and plus no concentration, then you can prove that this must be Hall, because the reason in the neighborhood you can always choose a small r, such that because the reason you have one term, no concentration like that. So you have one term, the total energy. So this is a small ball, B0. This may be less than epsilon. And if, so this is not true, you get a contradiction. By this is bounded, then you can hold continuous. You found a contradiction. So in that case, you proved U epsilon must be inside 1/2 and 3. So this is very important. Then you rescaling back, then you get the belong to the largest sky space. So in that case, in conclusion, we get so this is rescaling back. And the left hand is not depend on the second derivative. So this is W12. You use a Sobolev conversion. Then finally, so this is okay. Then you take limit. Then you get the total solution of because the reason you can converge into original Edison system, local existent. So this is the first part, the local existent. And the global existent, you still need you prove the global existent. You have a local existent, then how to extend it. Extended, then you also using this Lorentz-Scalia space. Then we study in this space. You can find out the solution always satisfy this energy inequality. So energy inequality. So and also you certify this local energy inequality. Local energy inequality. Then the local energy inequality is very important. You can extend it. If you start here, you can extend it by local resistance. You can extend it. Then so this means after your extension, then you have a concentration. Like before your concentration, you can get the original Edison least resistant, but like the liquid soft system also certify if initial. So here I think the mistake is something. So this is true. So this is integration from 0 t. But however, in some sense, we need to verify the space-time H2 norm is finite, and you need to prove that if the t greater than 0, they're always finite. So I think this is okay. You just integrate by parts like harmonic maps. It's no problem. So it's only thing. The second part you need to do a little bit of trick. The second part is means that if initial value in H2, but however, of course, you cannot initial value H1. I still can prove for any the tau greater than 0. I can prove this is finite, but this is a dependent tau maybe. So we can prove. So this is the constant might be dependent tau, but this is finite. So in that case, the finite is imply Hall continuous. Then you can prove partial regularity smooth is no problem. And how to do that part is something like you multiply the equation by this test function, then you do integration by parts. But of course, you're doing a covering argument. Then finally, you get this term. So this term, then you're using, I think my collaborator, he's very good. The Grover inequality, the Novistock, the trick, the Grover inequality. So using the Grover inequality, then you get this total bound like that, because the totally, so this integration in space-time already bounded. So this is bounded. So of course you always can find one. So this is bounded, and then everything. Then you're using equation again. So you get this bounded. Then you're using equation again. You get this bounded too. So this like a space-time second derivative also bounded. So in that case you imply. So now once you know in space-time belong H2, you know the solution is uniform Hall continuous in space-time, and also using gradient part, then you get this uniform for t time too. So you're using this Werner, Gagliardo, Nirenberg inequality, we can prove. So it's also uniform in t. So both uniform, then you get uniform for U2. Then you can prove U is a Hall continuous in C8, 1,8. That doesn't matter. It's not the best conference. It's not the best as the index. And but however, this part is tricky. But this part you can modify. I write an appendix, because the reason if you are Hall continuous in a liquid crystal, you can go back 3 dimensions. You do rotate it. You can such that U in one direction become 0, 0, 1. Then you're using 0, 0, 1. It means the third part of the difficulty is not the elliptic system, but how Z1 can zerb to the first 2 parts. Then finally, you can apply PD series, no problem. So that is one trick. And but you need a Hall continuous. Otherwise, you cannot do it. Then you can prove C1 alpha, then you will see infinitely. So that case, we use a modified case, we can prove. And so it's up to the final T1 is smooth. Is there any question or okay? Yeah. No, not finished. Okay, so now I come back. The second result. The second result is more complicated. So this is still modeling system. It's not. I just realized it's not the general model. Okay, so this Ellison Leslie system is from a mathematical point of view. So this is still complicated, but in physics it's still so simple maybe. Okay, so point out so this is complicated, and people know in 2D case Navier-Stokes is not a play major role. So you in fact you try to get this study, and so now is for originally you don't have this system, we already proved, and now we put together that cause a lot of mathematical complicated, and then you need the first. The proof, the results is similar like theorem A. We first prove local existence, right? So local existence, and then we can using local existence then prove this the continuous like maximum time. And the second step is you don't have concentration, then you need to density like you need to put the Navier-Stokes density together, and together no concentration. Then we also I think the idea is very similar, but however I must point out the local existence it's a sensing, but it's only a little bit different. We don't have a very nice local energy inequality. So if you look at Ginzburg-Landau approximation, so this one is a paper by Lin and Liu. They can prove the global existence, no problem. And then it's similar. We can do same trick. We can get a uniform the T1. They get a uniform estimate, the path limit. But the only thing different, you need this so-called local energy inequality. We don't have a local energy inequality for you must before concentration. We can control the energy, the T time by initial energy before concentration. So before the maximum time T, you have this log energy inequality. And the global inequality is true, but the log energy, so this is different. Because the reason this one is not true, you cannot prove the singular time is finite. The singular set is finite. So that is the problem. We cannot. I think I have one more. Okay, so in that case, we using the same trick, but it's very technical. And then you verify that case, you can produce the similar extension. You first prove the log resistant, then you do extended. Extended is one key part. Union said before this concentration, I still can prove. So the tau is greater than 0, any tau greater than 0. So this is a finite. So this finite means imply the use hold continuous. And then you using this Solonikov results, you can do iteration method. You can prove this solution is smooth. But this part, even you prove the hold continuous is not enough. You need to go to this condition. This condition is enough to using Solonikov. I read an appendix to say how to prove this go to regular. You need to do LP estimate, but it's no standard. But you still can do it. You need to do this the trick. You do the U value equal 1, right? Then you do the differential like 1. Then you always can control. So the one trick from this part is a key part. I didn't write detail. It's like that. So basically, you know U value equal 1. Then you differentiate. Then you differentiate. You get a U dot U1 plus U dot U2 plus U dot U3 equals 0. So if this U3 becomes 0, 0, 1, so this is the derivative you can control by first two. Then you can do, so you can, so the third one, you can control it by Z, then you can control. It doesn't matter is the system is elliptic or not, but you still can do LP estimate. So that case solves the problem. I think there is a key issue too. Okay, I think I finished. Thank you very much.
Question.